Okay, let me introduce myself. I'm Jan Sundermann. I'm from the Karlsruher Institute of Technology, the Computer Science Department. And yeah, I would like to report a bit about what we do there in terms of computer or storage intensive sciences. And we have a couple of storage infrastructures we operate for high energy physics and other non-high energy physics sciences. I would like to talk a bit about our use cases and our infrastructure. So for those who don't know where Karlsruhe actually is, it's close to Strasbourg and maybe 100 kilometers from Stuttgart and Frankfurt. And the University of Karlsruhe actually has a kind of special role because it was founded just 10 years ago as a merger of the former University of Karlsruhe and the research center, a former nuclear research center. And so we have both parts, the university part, but we also have the research center, where we have larger scientific infrastructures like big experiments. We have a synchrotron source and all those infrastructures which are not necessarily available at the typical university. The SEC itself is also 10 years old. It was also founded by merging the former computing center of the university and the research center. And we are there about 200 people. 60% of those are scientists, and we have roughly 40% technicians. So, as I said, we have a couple of infrastructures. We operate at SEC and KIT. So first, that's the GridCar, which is a grid computing center at Karlsruher, which is one of the computing centers handling the data of the LHC experiments at CERN. And we operate actually the German Tier 1 center in the context of the LHC computing grid. Then we have for other scientific applications, we operate what we call a large-scale data facility. So this is actually a storage facility which allows multidisciplinary users to store their data. So this can be users, this can also be instruments. I will talk about this a little bit on one of the following slides. And then we have another infrastructure which is called the Smart Data Innovation Lab. That's something a little bit different. So it's, the Smart Data Innovation Lab is a national research and development platform for big data applications. And there we partner with industry to provide state-of-the-art technologies for data analytics. So this platform allows basically users from industry to join with researchers from university and do their research on new technologies in a platform that's operated by kind of third party. That's us. So the large-scale data facility is a storage facility for a diverse set of fields of sciences. So we have climatology, we have photon sciences, we have a synchrotron radiation source, and they have microscopes, and they store the data in the platform. We have biologists, hydrodynamics. So these users can ask for storage on our platform, and then we provide them with what they need. On top of that, we also provide state service file storage for HPC users in Baden-Württemberg. So we recently set up a new storage system, and for that we migrated our old storage systems to the new system, which has a size of about 10 petabytes online storage at the moment, and a bit of offline storage and tape mostly for backups. And we used AFM to migrate these old systems, which with a size of roughly 3 petabytes to to the new system. We have a partner university, Heidelberg, where we have a fast interconnect, 100 gigabit link for just to allow users to ship their data between the sites quickly. We use a variety of protocols. These are mostly NFS and CIFS, but we also have a login cluster with SSH, and users can use SFTP to access their data. So, as I said, we have a variety of users. Some of them is just experimental equipment. There's an example here showing one of our clients. That's a facility. They operate high throughput microscopes, and they make pictures of zebra fishes to study the evolution of the fish embryos. And they use our facility to store their data. And also the facility is connected to our local HPC clusters to allow the users to do fast analysis of the data. At the moment, we use actually TSM for the backup, but we also have an HPSS installation, and we plan to use GHI in the future for backup of the data. Then we have a similar setup, and that's the Grid Computing Center Karlsruher. This is, as I said, a computing center for particle and astroparticle physics experiments. It's a German Tier 1 center in the worldwide LHC computing grid. There are in total 13 centers around the world, and we operate the German Tier 1 center. This is actually the application is a typical high throughput. So for the analysis of the data, we operated typical high throughput compute farm. So which means that we basically need a fast connection to the storage, but it's not like an HPC system where you need fast interconnects between the compute nodes. So the workload is usually a sequential read of the data, and also. So for that, we have about 30,000 cores in our compute farm. And just to give you an idea of the size of the compute we do, we had last year roughly 24 million jobs running 176 million CPU hours. So the system as we have now, it has a size of 25 petabytes on disk, but we also have offline storage, and the experiments also use it quite heavily, not for archival or backup of the data, but really as an extension of the online storage. And for that, we provide about 40 petabytes on tape in two libraries. Network-wise, we are connected with dedicated lines to CERN and all the other Tier 1 centers in the world. So we have here lines which provide 20 or 100 gigabits per second to our partners. Internally, we typically have all the technologies from 10 to 100 gigabits Ethernet in the compute nodes and also in the storage nodes. So this is the typical. This is how the data is generated. This is the picture of the CERN site. This is Geneva, and you see the Geneva Lake on top. And we have storage rings which accelerate photons and collide them inside the detectors. There's a picture of the ATLAS detector during construction. So these bunches of protons, high energy protons, collide and produce new particles which are measured and detected by the detectors. There's one picture below which shows the famous Higgs decay. And this data is then recorded to tape and shipped to the centers in the world. This is how the data taking basically works. So we have collisions with a rate of 40 megahertz. Each event has a size of 25 megabytes. So In principle, we would have to collect 1 petabyte per second in these experiments. So it's, of course, difficult. That's why and also most of the events are not interesting for physics analysis. So we have to filter those events, and there's a level of different triggers installed in the experiment, starting from level 1, which is pure hardware-based triggers, to level 3, which is a typical Linux PC farm. And in the end, we store events with a rate of 100 Hertz, which amounts to about 2 petabytes per year in experiments of raw data. And on top of that, we also have simulations and derived data for the physicists. So at SEC, we decided to buy a new storage system last year, in 2017, spring 2017, which is NEC GxFS storage appliance. So we wanted a system that could be used since we have to provide additional storage every year. We wanted something where we can add storage or file servers in a flexible way. The way we operate the system is, so we have spectrum scale order 2 at the moment. So we operate basically just a few very large file systems, which we can expand flexibly and easily. And we also need something that allows us to adapt to different use cases. So we have 4 different experiments which need tuning independently, and we also have the file servers which act as a node or as a connector to the tape libraries. So we need different tunings for those use cases. So the system, as it was installed, had a capacity of 23 petabytes, and also for us it was also quite useful as a blueprint for other storage installations we operate, like the LSDF. This is how it looks like. So we have a dedicated storage cluster with NSE servers, and we have several protocol server clusters, one for each experiment. And those mount the storage via RDMA of the remote file system. We have 2 independent redundant FDR InfiniBand fabrics. And those protocol server clusters are connected via 40 gigabit Ethernet to the grid backbone and the compute clusters. We have 2 routers, 2 switches for that, which have several 100 gigabit uplinks. This is how, as I said, we have this storage cluster, which is built up of several storage building blocks. This is just showing you how one of those building blocks looks like. So we have 2 NSD servers, which are NEC Express servers, and then we have redundant connections to stacks of 5 NetApp E5K disk arrays, enclosures, which 60 disks per enclosure. So we have 8 terabyte and 10 terabytes nearline bus disks here. And we have set up dynamic disk pools with 50 disks per DDP in a RAID 6 stripe setup to get the loons for the actual GxFS file system. And each DDP has disk space corresponding to 3 disks as a reserve capacity for fast rebuilding. Our protocol servers, they are separated from the storage system and do remote mounts of the file systems. Well, mostly we actually have in Gridka, we mostly have community-specific protocols, which are probably not known to many people here in the room. So the particle physicists tend to write their own protocols and own software. So we have to operate that, but we also have some standard protocols like NFS and GridFTP in operation. We also have a high HA test setup with NFS and also TIFF in the LSDF for the allow users to mount their storage directly. For the SSH, we build a custom CTDB setup to have failover of IPs between the different login nodes. This is what we learned so far from with the system. So we benchmarked it in the beginning to have a combined read-write performance of roughly 70 gigabytes per second. And so far we have seen that the experiments are actually using the system as intended. So we've seen it peak something like 50 gigabytes per second combined read-write performance. Just to give you an idea how the system is used, so we see something like 11 petabytes read from the compute farm and from remote on average per month, and about 4 petabytes write from the compute farm and the remote sites to the system. This is my last slide to give you an idea what we're planning with the system. We just recently installed new hardware. So we expanded the capacity from 23 to 34 petabytes and installed additional protocol servers. With the new system, we expect a read-write performance of roughly 100 gigabytes per second. And all this was also really nice to see. It was possible to expand the system just transparently by including the storage in the existing InfiniBand fabrics and just expanding the file system. So for the next years, we plan to expand the system by about 20% per year. So in the end, we will have in 2021 a storage system which is the size of almost roughly 40 petabytes. That's just as an outlook. And yeah, thanks for your attention. If you have questions.
How do you plan to deal with the licensing costs, spindle or terabyte in the future? How do you plan to deal with licensing costs?
Oh,
terabyte or spindle?
I don't have a good answer to that at the moment. At the moment, the licenses are at the moment, so there's contract, state contracts with where we get our licenses. Well, I cannot answer how this will continue. Sure.